Yeah. All right, everybody. Hello. Welcome back to the afternoon session. We have a planet-packed session this afternoon, kicking off with Ruth Murray Clay from UC Santa Cruz. She's going to be telling you more about clues to the history of Earth-sized worlds, a role for formation theory.
Thanks. I'm excited to be talking with you. I've been enjoying this meeting so much so far. So I'm going to start with a few thoughts that are neither original to me, either in general or at this meeting, and I also think are not very controversial, but I think nevertheless bear repeating. And the first one is just 25 stars can make a nice HR diagram, but we know that terrestrial planets are not going to be organizable in such a simple way. We know this already. As David Singh showed on Monday, even with 10 spectra of easy gas giant planets, you can look at those spectra. We don't know how to organize those spectra and what physical processes are generating them. And we know from the solar system that terrestrial planets are affected by a broader diversity of physical processes. So we're not going to be able to put 25 spectra in a line and know what terrestrial worlds are like. So Habitable Worlds Observatory will be a mission of exploration. That's what's exciting about it. We don't know what those terrestrial worlds are going to be like. And if we take the broad approaches to modeling that we have, either extrapolate from detailed modeling of solar system planets, which are just a few examples, or cover large possible parameter space with models that we know are too simple. We try to meet in the middle, imagine what we're missing, imagine the things that we haven't seen before. Doing all this is really important, but we know we're going to be wrong. It's just unavoidable, right? It's exciting. Yay, we're going to be wrong. It's great. Okay. Woohoo. Okay. Okay, so my non-controversial prediction, and tell me if it's controversial, but I really don't think it is that with 25 spectra of terrestrial planets, it's going to be really hard to figure out what's going on. Also, humans are bad at predicting complicated things that we've never seen, right? So, and biospheres are complicated. We only have one example, so never mind terrestrial planets. Given the broad uncertainty in what life is like, we really do need to understand what abiotic atmospheres are doing if we're going to have any hope of searching for life. So we need to organize all this, and we need to understand what's going on if we're going to do, the basic job of searching for habitable worlds. Okay. So what can we do about this? Well, we can have a bigger telescope and have a lot more spectra. I'm not opposed, right? But we can also really try to take advantage of all the information that we have at hand, and I think that we really should be doing that. So, so the upshot of that is that comparative planetology, planetary system context, they're going to be central to our search for habitable worlds. They're not just, nice extra physics that we can do with the observatory. I mean, I love planet physics, hooray. But it's not just nice extra stuff. If we really want to understand what worlds might be habitable, we actually have to do this. We just are not going to have enough information if we only look at the spectra. Okay. But, of course, sadly, but also excitingly, because physics fun, planet formation is not something that we understand well at the moment and is not well organized. In particular, we haven't yet been able to test the guts of classic planet formation through Jupiter and Saturn analogs. We have a lot of planets, but we don't have those. We really don't know if the solar system is rare. We know it's not the standard. It's not, everything isn't like the solar system. But there could still be a lot of solar systems out there. Is it one of several typical outcomes, or is it really rare? We don't know. But we do know, again, that there's not one simple outcome for planet formation, so much like if we want to understand what habitable worlds are doing, I think that if we're going to understand how planet formation is producing these worlds, we're going to need that context for the broad range of planets that we're looking at, not just a couple that give us our context. I mean, we just already know that it's going to be too complicated for that. So that's the upshot of what I want to say. I think we really need to see this as a central component of this mission. Okay, so let me take a step back and just remind us all about pre-exoplanets, how we thought planet formation worked. It's a beautiful picture. If it worked this way, maybe we would have some hope that everything would be nice, and even if everything was complicated, it would at least be similar across systems. We know that's not true anymore, but let's just remind ourselves, right? So we have some rocky planets on the inside, gas giants, ice giants on the outside. So you can understand this, and all of these ideas are, still around, still good ideas, and by using a couple of principles, right? So this is now my disk of solids. That's the brown. That's the star in the middle. As when you're close to the star, your orbital time is short. You grow fast through collisions of solid bodies. This is assuming you have planetesimals to work with. That's a whole other story that I don't have time for today, but of course that could be critical to this story. And if you have more material, that also means you grow faster. Okay? So let's put this on this diagram. As you go out in the system, you have longer orbital times. And in the inside of the system, you have less material. On the outside, you have more material. Just the circle is smaller on the inside. The circle is bigger on the outside. Let's stick on an ice line here, a water ice line. And now you can say, well, you have even more material on the outside because you have some water ice to work with. And you can build up these, the planetary system this way. And just to dig in just a tiny bit deeper, a critical component of this story is that the planet's gravity dominates within its Hill radius. So that's where the tidal gravity, tidal acceleration is less than the planetary gravity. So that's where you can have a moon orbiting, right? You stick a few Hill radii into your disk. That's where you can grab the material nearby you. This is called an isolation mass. You accrete all that gravitationally accessible material from the disk within several Hill radii. And now go back to our diagram. In the inner part, you have a small isolation mass, smaller than rocky planets, with a minimum mass solar nebula. Again, another thing that we know we shouldn't rely on. And then you need a late impact phase, like the moon-forming impact, to complete your planet growth. In the outer part of the system, your isolation mass is just small enough that runaway gas accretion takes a long time. In the middle, your isolation mass is big enough to accrete in a runaway gaseous envelope, and you have enough time to do it before the gas dissipates. Okay, so that's all nice. And just along with that, right, where does the material, we're interested in the compositions of our planets, right, if we're interested in habitability. So where's that material come from? Well, until it's incorporated into planets, and in planets you have all sorts of chemistry that changes things around. But in disks, most molecules are inherited from the interstellar medium, right? So you have what you have, and then which ones are solid or in the gas depends on if you're hot near the star, you don't have those ices. If you're out farther, then you can have the ices. Okay. So if we go back to this picture again, Earth, it's interior to the water ice lines. We're very dry. We have very little water, but we have a little bit of water that was delivered from afar. This is supported by D to H ratios, water on Earth, that it came from the outer solar system. But already we're seeing some stochasticity in here, right? If you look at models that people have made of how much water you're going to end up with on these planets, it actually varies dramatically from system to system, because you're bringing this little bit of a veneer of water from the outside, and how much you get has a lot of randomness in it. Okay. So, but of course, if we go and look at the planetary systems that we found, then this calls all of this into question. Not the basic physics, but the organizational structure into question. So we have gas giant planets found from radial velocities. They have really high eccentricities. Planets move around. dynamically through disk migration, through scattering, through tidal dissipation, through a variety of potential mechanisms that could be really important. Even in the solar system, we know that our giants moved around from the dynamical structure of the trans-Neptunian region. That was discovered at just about the same time that exoplanets were discovered. From the Kepler planets, transits show that super systems are common. We don't have any analogs. And then, of course, from direct imaging, we know that there are wide separation giants. And these are so far away that that formation model just doesn't work for them as is. You can make these potentially through gravitational instability if you want, if this is the tail of a distribution. But if there are a lot of these out there and, this is part of the giant planet population, then we need another way to make this work. So just to bring together some themes, right? Planets move around. Interactions between gas and small solids are increasingly recognized to be very important in this process. Planetesials may not form everywhere. Again, I don't have time to go into this, but this could be a critical component of this. And all of these have important implications for planet compositions, and are going to lead to different conclusions about what these planets, even in their bulk, are made of, never mind all of the detailed additional geophysics and chemistry that can affect them as they move on through their lives. Okay, so just to remind ourselves of a classic story that makes it gives me at least pause about taking what we know now about planet formation and assuming that we know what we're going to find when we look with Habitable Worlds. This is from 2005. Frequency of planets at the time, but they were really hot Jupiters, increases with stellar metallicity, right? Okay, but now let's take a look at, I'm just looking at giant planets here in the white, planet mass with semi-major axis. This is a set of RV discoveries. Around low metallicity stars, those giants are mostly all beyond 1 AU. High metallicity stars, those are the ones that go really close in. And so if you're looking at those easy to find Jupiters that early, when they were first discovered, those are typically around high metallicity stars. But why are they smeared in? Well, maybe they formed there, maybe they moved in, but they certainly have had some big dynamical to-do go on. And I don't want to live here where there's a gas giant planet with a really high eccentricity orbit hanging out at 1 AU, even on a moon around it, like eccentricity 0.4, right? That's not going to be fun, right? So this is from 2009, but it hasn't changed that much. These are the gas giants that we know about. None of them are what we're looking for, right? There's Jupiter right there. On the outside, zero eccentricity, like right at the edge. Okay. None of these are what we want. None of them. Okay, this is just another way of looking at this, where you can, go with semi-major axis and eccentricity, and you can see that there's a sort of higher envelope of eccentricities for the higher metallicity stars. So you can say, oh, well, we should look at the low metallicity stars. Maybe we should. But even those, they're still like Jupiter's, like over here. We don't know. We don't know what's going on with those systems. I do think we should look at lower metallicity stars if we have a choice. Okay, just really briefly for fun, because I have you. High eccentricity giants are higher mass. Like these would go out to like 10 Jupiter masses. They're like the higher eccentricity ones are the higher mass ones, which dynamically seems kind of weird. But if you actually say that disks that start with more gas giants are the ones that collide and grow through a giant impact phase into those big gas giant planets, then that collision growth process gives you high eccentricities. And this is a model with like very little, no fine tuning basically that goes into it. So I'd say these are pretty good matches. And you can even get this metallicity dependence from this kind of simulation. So basically, whether you believe this or not, as an idea, like these are systems that have a lot of mass and gas giants doing a lot of interesting dynamical things that are ratty places to find Earth. Okay. All right. So things move around, and we haven't figured that out, but the giants, which are the planets that we know are going to be the best tracers of planet formation, are not the systems we're interested in. Okay. All right, so that's this first thing. Okay. Also, so the second theme that I mentioned is, we now know that solids interacting with gas in the protoplanetary nebula is going to be really important for formation processes. And that just calls into question that whole idea of isolation. Isolation, as I formulated it in those classic planet formation theories, I think is dead. Or at least you have to resuscitate it if you want it. You have to have a reason why you're allowed to do that when we know that gas drag causes small solids. People often call them pebbles. They can be fluffy aggregates. They don't have to be like what we think of on Earth as pebbles, but pebbles to drift. So if you have like a large surface area to mass ratio, you don't feel as much gas drag in the nebula. The nebula has some radial pressure gradient that makes the gas disk feel like it's going around a slightly lower mass star. So you have your solids moving through that. They're going to feel gas drag. The bigger things will feel less gas drag. The smaller things will feel more gas drag. We can just see that observationally now in multi-wavelength images of disks. For well-coupled dust, larger particles drift inward more quickly, and you can see that disks look at different sizes at different wavelengths. So we know that this is going on. And if you go ahead and look at that from a planet growth perspective, you have a growing solid planet, then for certain sizes of particles, this can cause your growth to dramatically increase in rate. So this can allow you to form gas giants at these really large distances. That's one of the reasons that motivated this work. You need your particles to be small enough that they're affected by gas. So they're captured essentially by gas drag by this forming planet. But you also need them to be big enough that they aren't just pulled around the planet. Oops. They aren't just pulled around the planet as the gas moves around the forming planet. So it's a very size-dependent process. It doesn't have to happen, but when you're in the right regime, it's really hard to make this stop. So if you're going to make an Earth-sized thing, you have to understand why this didn't make it bigger, which is interesting. And this is just one example, but a number of groups have looked at this, and you can actually, for reasonable properties of disks, end up with similar sized siblings of super Earth planets that have sizes set by the process of pebble accretion, which stops once your mass is big enough that all of the available pebbles are pulled around your planet and no longer accreted. You can actually make a huge range of sizes with this sort of process. Because as I said, don't worry about the labels here, but just imagine that this gray circle here is where the region within which you can accrete this incoming green pebble. At that radius, your green pebble can be accreted, but a little small pebble would be pulled around. It would be too well coupled to the gas, pulled around by the planet. We call this flow isolation. And if your pebbles that are around are all very small because they've fragmented in the inner region of the disk, then you can be isolated from pebble accretion even at relatively low masses at or below Earth's mass. Okay. And so whether this is important for terrestrial planets is still a major open question. I will comment that the hafnium-tungsten dating system tells us that in our solar system, Earth's differentiation happened late. That's because hafnium likes to stick in the rock. Tungsten likes to, if it's hot enough during core formation, go down into the core of the planet. And so if you want to have a lot of tungsten around, then you need, if you form your planet early, you have your core differentiation early, then that can be before hafnium has decayed into tungsten. When it decays, it's still sitting around in the rock and you can have a lot of tungsten. Earth does not have enough tungsten. And this suggests that you're actually forming it at 30 million years. So that looks more like the classic formation theory. By the way, I didn't say this at the beginning, but when I give formation talks, I love to have a story to tell. But I explicitly today decided that I was going to lean into there not being a good story, because I think that's actually the most important point for habitable worlds. Okay. So if you're feeling confused, then yeah. Yeah. Okay. All right. All right, so how are you going to organize this? Well, we can try, right? We can say, oh, well, if you have more disk mass, you're going to have like more solid stuff. You can make more rocks in the inner region, gas giants, ice giants like ours. You have really big disk mass. You can make those really like dynamically excited systems we were talking about of gas giants. It turns out if it's pebble accretion that matters, it's not disk mass, it's the disk temperature. Temperature affects your composition that tells you how big you're going to make these solid things. So disk mass or temperature, those are different things. But either of them, conceivably, you could have like a thing here where you're saying more of it, you make sort of more big stuff. Okay, so what about the bulk compositions of super Earths? Well, if you're trying to organize things this way, which I know is going to be too oversimplified. Again, that's the point, right? Then you should have gas giants out there with it. On the other hand, if you made no giants, and so you sort of make your mini Neptunes outside the ice line and migrate them in, so our super Earths are really water worlds, then you shouldn't really have gas giants. Okay, there's some information about this now from several groups. This is one from Art O'Brien showing that if you have a super Earth in your system, you're more likely to have a gas giant than a field star is. So maybe we should be up here in this kind of regime, but we really don't know yet. Okay, so what does this tell us about the compositions of these planets? So this is a plot, and I'm going to criticize it, and I feel okay about that because I'm on this paper, about the C to O ratio that you expect for forming planets that has made a big impact in the field. I think this is a really important result, but it's also a very, very simplified model for relative abundances in solids and gas. So what this is saying is that your gas in a disk outside of the water ice line, but interior to the CO ice line in your disk, tends to be carbon rich. Your solids tend to be oxygen rich, comparatively. Side note, people often say, oh, well, this means gas giants forming out in those regions should be carbon rich. But actually, if you look at the metallicities of planets that are observed, they're all superstellar. Jupiter's is 3 times solar. You're adding a lot more solids than you are gas. So even just in this basic theory, most of the things should be oxygen rich, not carbon rich. Okay, that's a side note for those who think about these things. But the general point here really is that solids and gas do not have the same abundance ratios if you're between the major carbon, nitrogen, and oxygen carrier ice lines. Again, these are inherited from the interstellar medium. This is where most of those atoms are in disks. It's not the only place they're from. And making abundances in planets match solar or stellar requires fine-tuning because when you accrete gas and solids, they're set by different physics. So for gas giants, you're setting your gas by gap opening. For solids, you have extra separate solid accretion. They're even more, well, I don't know. They're also decoupled for terrestrial planets. There's no reason, even if we know the stellar relative abundances of things, the planets shouldn't have those same relative abundances. Whether it'll be this or not, I don't know, but because there's a lot more complicated physics that goes into the chemistry in disks, but it really shouldn't match. Okay. Interestingly, Jupiter, right now, with the new Juno measurements, you can actually draw a straight line through Jupiter abundances. So Carnotberg and Robin Wordsworth has suggested, does that mean that Jupiter had to form at tens of AU? Maybe, or maybe we just don't understand what the chemistry in these disks is doing. Similarly, the H 8799 abundances, they're similar to solar. Their stellar is unfortunately unconstrained, in spite of the fact that they're located inside of their expected CO ice lines. And I'll just give one example of the many, many different results about protoplanetary disk chemistry that complicate this picture. In the outer disk, solids are coated in ices. We saw that they drifted in and get bigger as they drift in. If you treat this with reverse cloud physics, using microphysics developed for cloud models in planetary atmospheres, you see that the bigger grains are actually more likely to accumulate CO than the smaller grains. And you can actually match observations of CO surface density and gas depletion, which are measured across a range of disks. And the reason I'm showing this at the point is that these all look different, and it depends on the age and on the turbulence level in the disk, all within reasonable ranges. But like the whole thing is a big mess. Okay, one last mess that I don't have time to go into. There are these two, like in the solar system, there are these two different like reservoirs of solids that have really different chemical abundances that are thought to, some of them have like the nearby supernova with the aluminum-26 more, and the other one don't. The idea is that Jupiter separated these reservoirs. I frankly cannot understand how you're going to get this to do this, but even in the solar system, carbonaceous chondrites are depleted by a factor of 6 in carbon. It's super funky in the ISM. Half of our carbon is in these grains that you really need to get up to like 1500 Kelvin or something in order to destroy. So why is, and Earth is depleted in it. Earth has no carbon in it. Like, what the heck? Okay, I don't know. All right, so maybe you deal it like with early heating, but you need to get that carbon into Jupiter because carbon is really enhanced in Jupiter. Okay, I don't know. It's not going to be very easy, is the point. It's all a hot mess. So are the atmospheres. I mean, okay, so what's the conclusion? The conclusion is we're not going to understand what we're looking at all if we don't understand this context. So I think it's really important that we keep comparative planetology and planetary system context central to our plans so that we have some hope of understanding what the guiding principles are, and we're going to have to figure these things out in conjunction with each other. And I'm just going to take 30 more seconds to tell you about something that we had, four of us talked about at lunch on Monday that's totally different, but I'm super excited about, because I'm super excited that we're here at a conference in person. Yay. Okay, there are lots of galaxies. We've seen this, right? There are tons of them. If you take like, okay, so this is who was at lunch. Okay, if you take this thing and you guess what should be in there, there should be a galaxy in every one of these. And then if you like look a year later, it'll have moved. It's like, can we measure the planetary radii using occultations of background galaxies? Okay, that's it. that's my simulation. Okay.
Thank you, Ruth, for a very entertaining and informative talk. Surely there are questions. Yeah.
Thanks so much for such a great talk. We obviously have a lot of work to do, and so where can we get traction on the comparative planetology now? What can we make progress on, and where should we focus?
Yeah, that's a great question. So there are a lot of different directions where the field is coming from. I'm really excited about just getting the basics from Roman, from Gaia planets potentially. So we heard from Scott, and I'm hoping at least that those two missions will at least give us a sense of what does the population of Jupiter, like truly Jupiter-like Jupiters, look for. In terms of getting traction, there are a lot of ways that we can turn some of these organizing principles into hypothesis tests, right? So like you can say, if there's a super-Earth, should there be a gas giant, right? And now that has been done, that can be done better. When you have a hypothesis test, you don't have to find all of your planets with as much confidence as you would have if you were just looking for things, right? You can say, do the stars that have the super-Earths have more RV trends than the ones that don't? So I think that we need to be, finding all of those places, and I think there are a lot of them, as well as continuing to look with ALMA and do these amazing disk studies, to find all of those little hooks that we can get. And there's a lot that's going on and can be done. I think we will know a lot more. But fundamentally, we're not going to have spectra of these planets until we have habitable worlds. So even as much as we can do, we still really need to look at the systems, is my opinion.
Thank you. That was so fun. Thank you. And I took a picture of this because this is like in the book, whatever, right, of memories that we're putting together. I'm sure you're doing that, Jason. Okay, so Evgenia Shkolnik from ASU. Okay, let's talk about the target list then for Habitable Worlds Observatory, and what are some of the parameters that we need to vary of the target list, which is a series of stars at the moment, about 160 stars that have been put together by XEP. Thank you, Eric Mamacek and Carl Stoppelfeld for that. And so I haven't looked in detail on that whole list, but if we were to assess a parameter space, maybe stellar metallicity or composition, stellar temperatures. I know we have inner working angle issues and all that kind of stuff to consider as well, but just from the planet formation perspective, should we do something special with that list?
So I admit that I don't feel like I understand just the technical constraints well enough to know what the wiggle room is in that list. Sorry, what? Well, I think that there are two separate things that we want to do, which is, vary all those parameters, right? Like stellar metallicity, for example, and stellar mass, and see how things vary across those. But then that's separate from, but we're going to need a lot of systems to be able to figure that out. If we're just constraining ourselves to sun-like stars with a limited metallicity range, and if we did that, I would say we would want to go to the lower metallicities, then not the higher ones. Then we might have more of a chance of being able to figure out what are the controlling parameters in those particular systems that determine the spectral properties of the terrestrial planets that we see. And with only 25 planets, I'm kind of thinking that probably the second is what we're going to do, even though as a planet formation person, I really would prefer the first. But I haven't thought about it enough.
There you go. We have a question from Caleb Sharf online, which is a fantastic talk. Do you think we can have any confidence at all in models that try to predict the rocky planet initial surface compositions? For example, are they going to be carbon rich or not?
I mean, are we going to have confidence that they're right? Of course not. But are they beautiful models that Vicky showed us? Yes, we need them. So, I mean, I feel like this is just a mental ambiguity that, I mean, we know this is an exploration mission. We need to be able to hold both of those ideas in our head at the same time. So those models are critical, but I would be surprised if they're going to be right.
By the way, Eric Mamacek, XEP and JPL. The metallicity, by the way, will basically be solar plus or minus 0.2 dex RMS. That's the thing to keep in mind. It's just random nearby FGK stars. My question was, in the context of precursor versus preparatory science, I want to know from your perspective, so how important are the masses and orbits beforehand, at the time? Imagine yourself in 20 years. We're starting to get these images, or 12 years, Jason. We're starting to get these images in spectra. What do you need to know and when and how accurately?
You mean before the observations are taken, or?
Yeah, I mean, do we want to have?
Well, aren't we searching for the planets with the mission though? So don't.
Yeah, but you need masses, right?
Yeah. Well,
how
yeah.
accurate
I mean,
do you need
right.
masses?
So the more information we have, the more likely we are to actually be able to figure out what's going on, right? And masses are a key parameter. I mean, I don't have an answer for you as to like how well we need to know the masses. Others have done better work on that than I have.
Phil Stahl first, and then Aki, and then I think we're going to have to cut it off for the sake of time.
Yeah, Phil Stoll, NASA. Your science seems to be driven by outer working angle. You need to be able to see. Do you want to put a requirement onto this mission's outer working angle?
I would love to.
Well, I'm asking. That's the question. What's the outer working? And that drives the trade between coronagraph and starshade.
Well, if we want, I think it's going to be really hard to understand the formation environment if we don't understand what the giant planet population, what the giant planet compositions of these systems are. And I think that if it's like this, where it's just outside Jupiter, I'm worried that that's not going to be big enough. We don't really know what the population of giants is empirically beyond that. I mean, I could say, well, I want 38U because that's the size.
So it's fair not to have an answer, but I wanted to get the question out there because that's going to be an important trade.
I agree, and I think it's really important to think about in this context. I think that, what exactly that number is, I think it needs to be, if we're going to do this right, well outside 5AU for a typical system.
And a stupid science question from a non-scientist. It seems like, ignoring M-class, that almost everything in our galaxies either got a companion star, is either a binary or has a companion large Jupiter. And if I go back to your chaos chart, what does that say about formations? Half of all the G stars are binaries, and 30% or 40% of all the G stars that are singles have Jupiters, and so it seems like that nature wants to have two big things all the time.
Yeah, and for binary stars, it depends on how widely separated they are. Right? If they're well separated, then you can have a similar sort of situation around each individual star. If they're close together, then it's absolutely going to affect these outcomes. In terms of Jupiters, I mean, there's a lot of different ideas that have been proposed over the years about why Jupiter has actually helped habitability on Earth. It's hard to evaluate that with a sample of one, but if Jupiter is stopping material from the outer system from coming in, it could be really important. So it's not necessarily a bad thing to have a Jupiter, but we just don't want an eccentric one at 1AU. And so I don't know. It's a good question. I don't know the answer, but I think that we need to look empirically. It's just too complicated to think of out of our brains.
Aki Berberge, NASA Goddard. Yeah, I heartily agree with you, Ruth. This is a mission of exploration for sure. A couple of things to emphasize, though. We're gonna get more than 25 rocky planets. So those are just, that's just for the ones in what we think is the habitable zone, which is obviously a theory to be tested. But along with that, we'll get lots of other terrestrial planets inside and outside. And another thing to remember is that, if you want to see further out in a planetary system, look at a more distant star. So, even with the same outer working angle.
Yeah, but I think, I mean, to the extent that we can, we need to see them in the same system.
Yes, that would be best. But then the practical thing is that Neptune is really faint. It's like fainter than the Earth. So it's not just the outer working angle that matters here. The planets get in reflected light, they get really faint as you go out.
That's a really good point. That's a good point. So I don't want to know what the right number is, but I think it's larger than 5. And we should figure out what it is. And you're right also about the different terrestrial planets, but I don't know, maybe I'm overly pessimistic, but I think it's going to be a big, exciting, jumbly mess until we figure it out, and we need a lot of information to figure it out.
All right, let's thank Ruth again. Okay, so our next speaker is Becky Dawson from Penn State. All right. So Becky, family portraits for planet formation.
Thank you. So a couple weeks ago when I was working on this talk, I was also packing for family camp, and an email arrived from the director with some final logistical information. And I saw at the bottom of their email, it said, as a reminder, you will have a special opportunity this year as part of family camp to participate in a mini family photo shoot with your group. So this reminder was actually news to me, and it meant that in addition to tracking down my 2-year-old's missing left sandal, that I would also need to find his missing button-down shirt. But nonetheless, I did a little fist bump because who couldn't use a free family portrait? And that's exactly what the SDDT report said as well. HabWorlds will revolutionize our understanding of planetary system, offering nearly complete family portraits and associated spectra of the menagerie of gas giants, Neptune, super-Earths, and terrestrial worlds. These family portraits will even be free, kind of, in that the same requirements that we might need to image mature exoplanet systems to determine planet and planetesimal belt locations are also what we need to find habitable zone planets. Of course, they're not really free, and what we meant by that is that with some of the right design requirements, imaging an Earth twin can allow us to characterize the rest of the system. So today I'm going to talk about some of the wish lists that might drive those design requirements and why it's so critical to characterize the rest of the planetary system, whether it contains an Earth twin or not. We're going to need a whole collection of family portraits to investigate both the processes of how planetary systems form and evolve and the history and habitability of individual systems. So our solar system is a great example of that, where every component of the whole system tells us about the Earth's formation and habitability. For example, the spacing between the Earth and Venus and Mars tells us about the formation processes and timescales. The orbits of the giant planets and the Kuiper belts tell us about early gravitational upheaval in our own solar system. And the physical properties and compositions of asteroid and Kuiper belt objects tell us about the processes of forming planetesimals and about radial transport in the nebula that may have affected the Earth's composition. So we can hope to learn similar things in the family portraits that we get from Habitable Worlds Observatory. Here's an imaginary system where we can start in the same way to piece together how the different components tell us about the potentially habitable planet in the system. So in this imaginary system, we have several terrestrial planets that have been discovered. They're water-rich, they're compact, they're in a resonant chain, and one of them is in the habitable zone. The habitable zone one has an inner debris ring that it's shepherding, and that gives us constraints on that planet's mass. And the composition of the debris ring also tells us something potentially about the rocky parts of the water-rich terrestrial planet. We see a bit of a gap between these terrestrial planets and an outer debris ring, and that, along with its orbital architecture, is telling us that maybe these planets underwent a little bit of migration, but not a lot. So that's probably not why they're water-rich. The more likely culprit is the elliptical Jupiter in the system. It's not too elliptical, but it's enough to offset a debris ring and may have scattered in some of this water-rich material that are detected in the spectra of these terrestrial planets. So we need a collection of planetary family portraits like this, and the questions that I want to get to in this talk are, how many portraits do we need? How much detail? Can it be more of a sketch, or do we need a real portrait? And which family members do we need to be sure to include? Right now, our family portraits of exoplanet systems are very incomplete because each discovery technique is looking at different regions and at different systems. So we might know about the compact inner planets in one system, the eccentric gas giant planets in another system, and just the debris belt in a third system. And recent and upcoming surveys are allowing us to look at the same systems with multiple technique and are helping fill in the portrait, but are still incomplete. So maybe in 2015, we knew from K2 about some system that had a close-in super-Earth orbiting a bright star. Maybe in a few years, we'll have characterized that planet's atmosphere with JWST. We'll have detected some tentative signals from ground-based radial velocity of slightly further out planets. And we'll know about a giant planet in the system from the combination of radial velocity and Gaia. So that'll be a big improvement, but we still are missing critical information about this system. Of course, we haven't even probed the habitable zone. Maybe it's a system where that outer giant planet we see formed much further from the star and underwent a lot of migration and shaped the debris belt in its process. Or maybe it's actually filled in and there's some water poor super-Earths in the habitable zone. Maybe the giant planet is water rich, formed kind of near where we see it. And then there's this large extended debris disk beyond that where planet formation failed. So we need to have the complete portrait to see what's going on in these systems. Without these portraits, the basic questions of planet formation remain unanswered, including who is in our planet family portrait, what processes form planets, when do planets form, where do planets form, why do planetary systems differ from each other, and how does planetary system formation play out? So I'll now talk about in a bit more detail each of these questions and the observational wish list for trying to answer them. So for who is in our family portrait, we're aware of all these different types of planets that are out there, but does planet formation typically establish zones of planet type within an individual system, like in our solar system where we have terrestrial, gas giant, ice giant, and debris belt? Or do mixing and migration processes dominate so that there's a mix and match within each system? How do giant planets affect the presence and properties of terrestrial planets? Do compact close-in systems like were discovered in abundance with Kepler deprive the terrestrial regions so that they're mutually exclusive with habitable zone planets? And do rocky habitable zone planets exist in special types of systems, or are they more widespread in different types of ecosystems? So as an example, as we look at this big collection of portraits, we might see that there are different flavors of systems. And maybe we start to see that having a giant planet in the system actually facilitates having rocky habitable zone planets. And there are other systems that have compact close-in Neptunes and outer belts, etc. Or maybe systems aren't really sorted into flavor and they're more mix and match, and maybe Earths go hand in hand with all different types of systems, and the giant planets are just a bonus that don't seem to have a detectable effect. There are many other possible outcomes as well, but we need a whole collection of systems to be able to tease this out. So how many portraits do we need? I'm going to suggest that we should aim for at least 100. And part of this comes from, we needed dozens of systems to see, for example, the peas in a pod similarity that we've mentioned. And we need that number of systems to be able to see rare outcomes, like something new but that's as rare as a hot Jupiter, which can be very powerful in distinguishing competing theories. How much detail for planets? I think we definitely need the mass, which could maybe come from stellar astrometry if it's not available from ground-based radial velocity. We want to know what type of planet it is, at least roughly. Is it a rocky planet? Is it a Neptune? For the debris belts, we'd like to know their location, the rough radial extent, and ideally something about the morphology. Which family members? For this broader survey, I would say for planets, at least down to Earth mass, and for debris, at least as faint as asteroid and Kuiper belt analogs. And weighing in on this question that we had about the working angle, I think it should be large and ideally go out to 100 AU so that we can see free outer planets, those that are at least detectable. There's definitely some room for debate about that exact number, though, I agree. All right, so what processes form planets? Ruth gave some wonderful information about some of these different proposed processes we have for growing from dust all the way to full-fledged planets, that there's still a lot of debate about which of these growth processes dominate at different sizes. And when there's more than one possible way to grow, is it the same within regions of a single system? Is it the same across system? Do we have one system where planet formation works like this and another where it will look like that? So a couple examples of something we might see. In our first example system, we have sort of two different areas of the system. One has rocky planets. There's an outer part that has water worlds and an asymmetric debris disk that might imply some gas disk migration. Planets are fairly self-similar in size. So this looks like a system where maybe there was pebble accretion happening and it led to different sizes in different parts of the disk because of the disk condition. In our second example system, we have a more stochastic looking set of rocky planets, an outer giant planet, a water-rich debris belt, and the rocky planets have this thin layer of water on them as well. So this looks more like a giant impact formation scenario with late volatile delivery. And so it may be different in different systems, which we start to really uncover as we get a collection of portraits. So to probe these formation processes, I think we need a deeper set of family portraits, maybe about 30, like 10 that have rocky habitable zone planets, maybe 10 that are adjacent, so like a rocky planet that's not in the habitable zone, or a super Earth or Neptune in the habitable zone, and maybe 10 wildly different systems. For type, we want a deeper knowledge of their composition from the spectra. For the debris belts, we'd like to know more about the width and morphology. And for these deeper portraits, I think it would be very helpful to be able to go down to Mars mass so that we can see the formation process playing out below the mass that we're most interested in. As was mentioned this morning and in Aki's talk, we can also be learning even more about our solar system's family portrait by learning about some of the smallest members and searching for very small Kuiper belt objects that can tell us a lot about the process of forming planets and planetesimal formation and distinguish some of those competing theories. All right, so where do planets form? Some of the questions we have are planetesimals or planets preferentially formed at certain locations like ice lines or pressure bumps? Where do different types of planets source their materials, and in what form, dust, pebbles, etc., does that material get accreted? Where do Earth analogs get their volatiles? To what extent do full-fledged planets migrate? How far out do planets form, and what's the typical scale of a planetary system? So a couple examples of things that we might see. Maybe we see one system where there's sort of a water world region of a few water worlds, and then there's an outer region that has carbon-rich gas giants, and maybe these correspond to a couple different ice lines that were preferred places of formation. And maybe in another system, everything looks weirdly carbon-rich, and maybe there was a big planetesimal factory happening at a particular ice line that made basically all the planetesimals and then sent them in to go into planets. So this compositional information will be really important for understanding where planets form. Now for how much detail, we want even more detail about the planet from its spectra, things like atmospheric C/O ratio, bulk density, which probably means getting a radius somehow, detection of low mass atmospheres. For the debris belts, we want to know more about their color and composition. So when do planets form? We want to know how early planetesimals form. When do different types of planets form relative to the dispersal of the gas disk? Does the transitional disk stage halt or trigger planet formation processes? So a couple examples of what we might see if we're looking at, for example, young debris disks over time at some different ages. In a more classic theory of coagulation of planetesimals and giant impacts, we might see the formation zone marching outward with time. Alternatively, we might see that there's an era, a universal era of terrestrial planet formation that gets triggered by the gas disk dispersal. So we see tons of dust at really young ages, and then everything's pretty quiet after that. And all the planet formation is happening across the disk instead of moving radially outward. As we've heard about in some of the earlier talks, Habitable Worlds Observatory will give us new views of the inner regions of protoplanetary and debris disks. Even with some of our favorite systems, we're now going to be able to look in the terrestrial planet region and see what's going on there, what kind of features and morphology and colors and compositions we see that can tell us about the planet formation process in these systems where we already have a lot of wonderful information about the disks in the outer part. So how many portraits here? I would say it'd be great to get at least 20 young systems with a range of ages, and systems that don't necessarily have planets there. We might, in this case, be just as interested in systems that haven't formed their full-fledged planets yet. So another question is why? Why do planetary systems differ? Why are certain types of planets common or rare? For example, we know super-Earths, inner super-Earths are common, hot Jupiters are rare, giant planets are 10%. Why is that? Do some systems fail to form any planets? And if so, what prevents the formation? And how do mature systems differ from each other in terms of total and radial distribution of solids and of volatiles? For example, we might find as we explore that some systems have it all. They have compact inner systems, they have rocky habitable open planets, they have gas giant planets. Other systems only have debris belts. I mean, debris belts are great, so maybe it's not a bad thing, but there might be quite a range in terms of the inventory of what's in each system. So now we want to add systems without planets to the group so that we can see what is there, and cover a diversity of stellar types. And I think it will be very helpful to have mass detections for planets that can't be directly imaged. For example, planets that are within the inner working angle, which may be possible either with ground-based radial velocity or with stellar astrometry. Then how does planetary system formation play out? How much mixing occurs at each stage, from radial drift of materials within the disk to much later chaotic evolution where planets themselves are being flung around? And how do giant planets influence smaller planets' formation and properties? We saw with this imaginary system the power of detailed orbital characterization of the planets, like that we knew the system had a chain of resonant planets, and with connections between the orbits and the composition. So knowing these were water rich, like really aided the interpretation, again, of an imaginary system. So for this question of how, this kind of further motivates having a big survey of family portraits, because this will also help us see planets that are out of place. Like maybe in most systems, the rocky planets are here, but in this system, it's somewhere else. Or we maybe see systems that overall look pretty orderly with zones of different types of planets, but then there's one random planet that's been flung so that it's nowhere near where it formed. So having enough systems will let us detect situations like this. It'll be very important to have precise 3D orbital characterization of the planets, including of the planets that also have detailed compositional information, so we can use both the orbit and compositional information to piece together the story of what happened there. And it'll be helpful for the debris disk to have more detailed morphology, asymmetries, scale heights, things like that for systems that are a bit disturbed, like where we see planets that look out of place or that might have more inclined or elliptical orbits that seem to suggest an upheaval there. All right, so I took some time to think about how a portrait session could go wrong, both in preparation for our family camp portrait, but also for this talk. So one situation that I could think of is that we might have critical information within the inner working angle or outside the field of view as we're trying to interpret the system. For example, we might have a scenario where there's a planet that we're not detecting that we think may have scattered in or out material that has a really important influence on the composition of the planets that we see, but we can't detect that planet. So how can we try to mitigate this situation? The inner working angle everyone is very aware how critical that is, but also having a large outer working angle will help us get a more complete inventory. And having stellar astrometry or other methods to see what planets are there that we couldn't detect through direct imaging so that we at least have a hint that they're in the system. Another situation I could imagine is that we have some really cool looking emerging trend, but there's just not enough systems to say it's really significant. Like maybe we're starting to see a correlation between water content of terrestrial planets and the presence of outer gas giants, but there just aren't enough planets in the sample. So having more planets in the sample would be awesome. But another thing is to plan to observe adjacent systems that can tell us about the same processes. So for example, if we're short on terrestrial planets, let's look at other systems that have giant planets and see how those giant planets affected the composition of the other planets so that we can try to piece together a story. Another situation I can imagine is we can't characterize the atmospheres of enough small planets. I'm thinking here like we don't have enough telescope time to do that, and we're not sure which small planet to prioritize. Maybe I'll show in a moment like the pyramid of prioritization. So another thing we can bring in there in deciding which ones to really hone in on is to look for trends in architecture with larger analog planets. For example, if we see very water-rich Neptunes or something where it's easier to do the spectra are in this type of system, maybe that's the type of system we also want to look at rocky planets in our priority list. Another situation I can imagine is that we have insufficient resolution on the debris belts. Like we know there's a debris belt there, but we don't really know where it is, how wide it is. For example, we might have a situation where we see some dust, but we're not sure if it's coming from a local population of asteroids or if it came from somewhere else in the system. So it'll be really helpful to have a sample of young debris belts that are more massive and easier to characterize so that although things might change from those young systems to later on, I think they won't dramatically change enough such that we still can get a sense for where debris belts are when we use that younger sample. Then a final scenario I thought of was mix-ups. So like we see a signal, but we're not sure which planet it's coming from. One way to mitigate this is to just have a big collection of planets and be able to do some population-wide analysis like hierarchical modeling where our knowledge of the population is going to really inform our interpretation, aid our interpretation of individual planets. So this also speaks to having as large a sample as possible. So how do we, what kind of survey strategy helps with this? So there's this really great pyramid prioritization scheme. I think I took this from the Luba report. I think there's a similar one in the HabEx in terms of how do we find life, prioritize planets to look for life. But I think in terms of these detailed family portraits that we want more of a upside down Terray style where we do a detailed family portrait for many systems and then for a few we do more of these spectral deep dives. Of course, that's going to require a lot more survey time. So one question I have is, could there be 2 habitable world observatories? Because it seems like a lot of the cost goes into developing it, and that it's relatively cheap to have the second one. I know there's a lot of reasons that this might not be feasible, but if we're going to be really short on time, which is what I'm quite worried about, that we have the capabilities to do what we want, but we don't have enough observing time, then having 2, of course, would be really helpful for that. So I'll leave you with these questions and then with this wish list. Thank you very much.
Thank you, Becky. And I, for one, would gladly take 2 habitable world observatories. No, why stop at 2? Okay, I see Aki.
Aki Berberish Goddard. Thank you, Becky. This is a very thoughtful talk. I appreciate it. Okay, so about the two HabWorlds. That's why have 2? Why have 1 when you give 2 for twice the price? No, but the idea that we are going to go all in on servicing this observatory, and it's going to last, hopefully, knock on wood, it will last for decades, like Hubble or Keck. I think maybe you can have what you want over time.
Yeah, that's a great point, and seems like I'm guessing there's a way to factor this in, but we need it to last for a much longer time via prioritization, like having the survey time like really affect the design choices.
Yeah. And the other thought I was saying, though, I was thinking of is that it seems to me that there's some roles for other observatories in getting us all this information. I mean, some of this stuff is actually just either incredibly difficult for HabWorlds, or maybe there's actually something that's better suited to do it. Like what role can ALMA play in filling in some of this information, or what role could an Origins-like mission fill in for some of this information? It would be good to think about that too, I think.
Yeah, I agree. Particularly in terms of characterizing what's happening at the heart of the planet formation stage. Yeah.
Thanks for a great talk. I totally agree with your wish list. I think it's wonderful. Mine is more of a comment, which is that this is probably the 4th talk, I think, now that has sort of embraced this mantra of we want all the planets, right? And I think we would be missing a tremendous opportunity if we didn't embrace that mantra. So I'll just note that, there are certain technologies that can get us to this point, but they're going to require investment. And there are certain technologies that are higher TRL, but you have to pay a tremendous penalty to be able to do these observations, either in terms of exposure time or number of observations or something like that. So this scientific thread that we've heard now through the conference, I think, is something that we should keep in mind, on Friday when we talk about technology development.
All right. Saw 2 more hands, and then I think we're going to have to cut it off for the next speaker.
Hi, Becky. Great talk. Andrew Vanderberg, MIT. You mentioned an astrometry-based way to measure masses for planets, and there have been a couple of other talks that have mentioned this throughout the meeting. I'm wondering if that would be a good opportunity for a precursor, separate small mission to be able to go and identify these planets using astrometry, which is much less vulnerable to stellar activity than precise RVs are.
Yeah, I think there's been some thought to how to do it on board with LUVAR, but I could see motivation for a precursor mission as well. So I haven't thought in detail about what the requirements would be for that. But I think that's an interesting idea. Yeah.
Yeah, great. Again, great talk and great list here of initial requirements, but categories. I think what's really important is to think about how we connect your theories of pebble formation and other factors with actual quantities that we might, break points that we might want to look for. Because when you set the requirements for, say, bulk density or atmospheric C to O, you want to be able to set the requirements on the level and the precision that you get to for that. And I mean, this is a much broader sort of point to everyone, which is the hardest part of a science traceability matrix is that exact jump between a quantity and the precision on that quantity to prove or disprove a hypothesis. And so hopefully we have some more chance to talk about that tomorrow when we're thinking about community activities on how we work together to jump from the quantity to the precision we need in that sense, because that will really help the requirements flow down for observatory preparation. So.
Yeah, and I think one thing that I've been thinking a little bit about, but I'm not really sure how to go forward with, is like what Ruth mentioned about exploration. Like, I think if probably any hypothesis that anyone has right now is going to be wrong, and setting a precision based on that like makes sense, but also we want to think about what precision we need to be able to explore new things that we can't even think about, which I think could be a little challenging to quantify, but I'd like to try to do that as well as part of this.
All right, great. Let's thank Becky for the excellent talk. Okay, so our next speaker is going to be virtual. Tiffany Kataria at JPL, who will be talking about assessing conditions for the origins of life with Habitable Worlds Observatory. So let's see. I think she needs to share her slides on there somehow, and I'm not sure how to make that happen.
Okay, I'm trying to. Can you guys hear me?
There's your screen share.
Okay, great. How about that?
Good.
And you guys can hear me okay?
Yes, we can hear you.
All right, take it away,
Okay.
Tiffany.
All right. Okay. Thanks, everybody. And thanks for, providing the virtual option. There are just so many events and, things things going on this summer that I couldn't unfortunately attend in person. So, but I'm very excited to be able to talk with you about what I would consider to be, a newer avenue of research for me. So I'm really excited to talk about it. All right. I wanted to briefly thank my collaborators there. I'll bring up a couple more of them over the course of this talk. All right, so let's dive right in. I like to start off in terms of contextualizing, origin of life, and it's, where it kind of fits in this overall strategic picture in bringing forth the Astro 2020 recommendations, which of course I think we're all very familiar with. So this, of course, is the Worlds of Sun in Context, which is most relevant to exoplanets. This is just a screenshot from I believe the webpage summary of each of the major themes. And so I underlined here one of the sentences from that summary in that, the search for biochemical signatures of life will play a critical role in determining whether life exists elsewhere in the universe. I think we can all appreciate that. But the argument I would make is that, the paradigm and the way in which it's been phrased, misses this, what I consider to be a crucial component in the origin of life. And so my goals for this talk today are just really to introduce origin of life and how it could fit within exoplanet science within the terrestrial picture, but also introduce how origin of life could be considered in the context of HWO and the design or the observations from the mission. And so before I dive in there, I bet you didn't maybe guess that you'd see some DNA and RNA today. But a big resource for understanding the origin of life for me has been Lori Barge, who's a scientist at JPL. Some of you may know her. She's a world expert in all things astrobiology and origin of life. And so a lot of what I've learned, I'm continuing to learn from her. And in conversations about, conferences and so on, the origin of life itself and how you define it is somewhat of a maybe hotly debated topic. But anyway, I want to be clear on what our definition is here in terms of how we think about it and the study that I'll be talking about later on. The basic idea of transcription and translation that takes you from nucleotides from DNA into a sequence of amino acids to build your desired protein. So it is a critical, pathway for forming life. And so this is the assumption that we make when we kind of think about life, or the origin of life, I should say. Okay. All right. And so just something I want to highlight is the fact that, Earth and its life have evolved together. They haven't been operating in a vacuum. The processes by which Earth and its life have emerged is a really, coupled process. And so here on the left, I'm showing you a cartoon here just from Wikipedia, but it's illustrating very nicely the different epochs on Earth as they relate to the emergence of life on Earth as well. And so you can see here from the, event at which Earth becomes oxygen rich and so on, and forming more complex life. I would say that the history of life on Earth is also tied to the history of oxygen. So over here on the right is another cartoon showing the rise of oxygen over geologic time. I'm sure you've seen a version of this at various points, maybe in Vicky's talk yesterday. And so here I just want to point out that the origin of life took place in a time when there was no oxygen present. And so Earth evolved in oxygenic photosynthesis, and other life evolved in the context of that rise of oxygen. And so the question I would like to pose is, what would this timeline look like on another world, be it in the solar system or outside of it on an exoplanet? Here's a timeline of the origin of life on Earth as we kind of think about it. So this is from a paper that Lori Barge led in 2022. I'd encourage you all to read it. I think it's a really nice, it's not too long, nice kind of overall summary of kind of the considerations of origin of life in the solar system and potentially outside of it. So this is really contextualizing Earth in the context of how origin of life emerged. And so I want to point out first that origin of life, which is kind of denoted here as an event, it isn't really an event, right? It's a process that takes you from the formation of the Earth to the first evidence of life. And backtracking a little bit, I want to also point out the last universal common ancestor, or LUCA, which some of you might have heard of. It's called, the root in the tree of life. And so origin of life is really the beginning of life, whereas LUCA is the life as we know it. And so those two things are distinct. I want to point that out. And so LUCA here is just what we know of with regards to our understanding of life, but there could have been pre-LUCA genes or enzymes that may look different from what LUCA exists today. And so there could have been many pathways by which life could have formed, but this is just the path that Earth took. And so in the sense of, how life might emerge on another planet, we can think about potential other LUCA, pre-LUCA pathways. In terms of how the origin of life is investigated within the community, there are generally two approaches here, the top-down approach and the bottom-up approach. And so the top-down approach pertains to, taking modern life as we know it and trying to infer evidence of LUCA or pre-LUCA origin of life, working backwards essentially. And then the bottom-up approach, which really utilizes laboratory experiments to investigate prebiotic chemistry in conditions that are relevant to early Earth. So I want to point out the logo here, the Origin and Habitability Lab, which Lori Barge co-leads with Scott Pearl over at JPL. They largely adopt this bottom-up approach in producing these experiments. Ideally, of course, both of these approaches should meet in the middle. But there's a lot of rich, interesting science there, regardless of what approach is being taken here. Okay. Various environmental settings have been proposed for the origin of life. I think this is another topic that is, there's definitely a lot of conversations taking place on where that could have occurred, which is maybe good news for us and studying exoplanets, right? It means that there are plenty of environments where life could originate, right? It makes it easier for us, maybe. So Lori Barge and her lab, the OHL lab I was just mentioning, they focus a lot on hydrothermal vents as a site for early Earth. For the origin of life. I do want to point out, actually, when it comes to hydrothermal vents, what's interesting there is that in early Earth, the ocean was largely anoxic, very rich in iron, and so, in fact, understanding hydrothermal vents and the emergence of life in that context is still very different from what modern Earth looks like today. But here are other pictures of where origin of life could have emerged. Some leading theories, Yellowstone, for example, a lot of these hot springs. Pumice apparently is a very good proposed vessel for the origin of life because it floats on a lot of volcanic surfaces. Same goes underwater volcanoes, of course, and then finally lightning. But really, ultimately, life can use almost any energy source. So, life finds a way. I'm sure somebody probably said that already, but it really does apply here. Okay, so kind of taking all of that together, this is at least my perspective for, how origin of life can fit within the context of our understanding of habitability, which I'm sure Vicki talked a lot about yesterday. And so from my perspective, the conditions for origin of life can be complementary, but perhaps separate to these conditions for habitability. And so in order to deem an exoplanet potentially inhabited, you should, I think, also evaluate its potential for the origin of life, because it's possible to have habitable yet uninhabited environments. Environments could have had origin of life conditions, but don't have origin of life conditions any longer. Venus may be an example of this. And origin of life I would consider to be a small subset of habitability in terms of perhaps its criteria. I think I've already mentioned in the geologic context, it could be considered a paleoscience of sorts in the context of exoplanets. It could in fact help us, our understanding of origin of life on exoplanets could in fact help us rule out false positive scenarios for habitability. And because they're arguably more stringent criteria for origin of life than for habitability, the idea that we could identify a planet that has the potential for origin of life will make it even more likely to guarantee habitability. Here below, I just wanted to highlight an astrobiology strategy report finding related to the origin of life. Planetary conditions that may be habitable today or in the past are not necessarily the same as those that could have fostered the emergence of life, and both are important for the search for life. So this is a lot of ongoing work, very active amongst our team that I showed in the slide. But I wanted to bring to you a kind of visual representation of what I've been talking about. This is definitely a figure in prep. I've got a summer intern working with me, Finnegan Keller, who's an undergraduate at Brown University, and he's diving deep in origin of life literature and exoplanet literature and working hard to synthesize the two and provide a picture for kind of a path forward in understanding origin of life in the context of exoplanets. And so this is one of those figures that we've been working on to try and illustrate how origin of life fits within our current paradigm of habitability. So this is a three-prong Venn diagram showing worlds that could be habitable versus those that could have had either past or present origin of life potential. And then we've attempted to place various solar system and exoplanet objects within that context. I think we could probably argue about a lot of these. I think anytime I've shown this figure, it's, everybody points at different things. You'll see that Europa is in multiple areas because we just don't simply know whether or not Europa is habitable or if it could have the potential for the origin of life. But I hope Europa Clipper will do a lot to demystify a lot of that. Titan also similarly is on different areas of this figure. And then you could, go through an exercise of trying to place your favorite exoplanet, terrestrial exoplanet in this figure as well. But the idea being that, we'd love to have a taxonomy that includes origin of life as part of this consideration. Okay, I'm looking at the time. I know I have trying to keep things brief here. There's a lot to dive into. But all I want to point to with regards to this slide is the fact that the idea of this biosignature threshold, which Lori puts forth in this 2022 paper, the idea of whatever metric we'd like to use to classify detection as biotic versus abiotic, life versus non-life. And we talk a lot about this, of course, in the context of biosignatures, but how can we also consider that in the context of origin of life? And so here on this kind of spectrum is showing you A through E. These are all things that have been generated in a laboratory completely abiotically, completely completely in absence of life. And then, of course, we've got life here on the most sophisticated spectrum here on the end. So if we were to consider two different worlds, a biotic world like Earth that has life, that we know has life, versus a prebiotic world that has minimal biology as far as we know, the threshold by which we can take a biosignature of a signature of life and say, okay, this is due to something biotic, the threshold for that on Earth is a lot lower, right? Because we know Earth exists on Earth. So if we see something that's related to life, we can say, okay, it's probably, very likely to be related to life. But if we see a similar signature on this prebiotic world where we don't really know what the biology that could exist is, the threshold for biosignature assessment is a lot higher in the sense of we want to rule out all the false positives. So I would say that our understanding of the origin of life is very similar in terms of biosignature assessment, right? Ruling out false positives. We want to better understand what other ways that life could, or that these processes, that these things could be produced abiotically in these different environments. So here are just some questions that I've been thinking a lot about. I won't belabor these points. I already mentioned biosignature threshold, but I'll just mention that minerals and geochemistry really play a role in our understanding of the origin of life. It's very much a coupled system, and so understanding the biogeochemistry really of oceans, rock, and ice, and so on is important for solar system bodies like Enceladus, but of course exoplanets. So I know I'm closing here on time, but I just want to sort of wrap up here with a couple slides motivating how this could potentially fit within the context of HWO. And so this is a pyramid, inverted pyramid. I'm sure many of you have seen this from the Louvois report in terms of how you might assess life on an exoplanet that could be observed with the survey. And so, from the top down, you're asking more, detailed questions about the system. Of course, are there signs of life? Are these signs of life robust? And what's the atmospheric context? And so I would say that assessing origin of life with HWO would likely fit within this these sort of lower, deeper tiers. And perhaps depending on the pathways by which origin of life emerge, maybe there are kind of offshoots in terms of, looking for different signatures or having different contexts to better assess how the potential for origin of life on an exoplanet. I'll very briefly just call out this paper from Claring-Bold et al. 2023, highlighting that pre-biosignatures, that's the term they use, could be detected with JWST and, relatedly with HWO. So these are a lot of species, many of which you're probably familiar with from some of the recent exoplanet detections with JWST, but they're also, relevant for biology and for origin of life. I'll just skip ahead to this, just briefly plugging an approach that we're taking at JPL to try and understand the origin of life in the context of exoplanets. Starting from our understanding of the minerals that could catalyze some of these essential chemical reactions. So this is work that actually Yuck Young has been doing in the context of a lot of solar system terrestrial bodies. Linking those minerals that could be then related to origin of life reactions, but then taking a laboratory and a modeling approach to understand not only the reactions themselves for many of the CHNOPS elements, carbon, nitrogen, oxygen, phosphorus, and sulfur. We don't understand a lot of how that chemistry proceeds, and so testing that in the laboratories is important, coupled with an approach that takes into account the entire closed system, the atmosphere, the ocean, and then the geology. And then, of course, trying to link all of that to HWO. So a tall task, it's still work ongoing, and we're really just trying to refine the phase space by which we could think about the origin of life for HWO and future missions. But ultimately, I think we can all agree that the search for life is a complex set of trades. A holistic treatment of exoplanets, as this closed system is very important. I'm sure Vicki may have showed this figure yesterday. But of course I want to highlight it here. I also want to highlight this other figure from Pranier et al. 2020, which highlights different different disciplines in terms of the understanding of what is life. I think there's a lot that we as a community can fill out in this physics and astronomy sphere. And so I'm really excited to embark upon learning about, what we are investigating what we can learn about the origin of life via HWO and other future missions. So with that, I'll take questions. Thank you.
Thank you, Tiffany, for the great talk. Are there questions?
Hey, Tiffany, this is David Chiardi.
Hey.
Nice talk. Thank you.
Thanks.
So can you comment on, so there is possible for a world to be prebiotic and yet it hadn't evolved to have life that we know of, and then it can be periodic and then it has stalled out and died.
Mm-hmm.
And so are there observables, testables, requirements, something that we can understand to understand the difference between something that hasn't gotten to where we are yet versus something that, died out and therefore actually is not likely to produce habitable worlds versus being potentially previously habitable? Does that question make sense?
Yeah, and I'll go back to actually the slides. I think a couple slides back. I'd say Venus is a good candidate of this, right? Something that probably had the conditions for life in its past, or could have had the origin of life in its past, but could have been prebiotic and isn't anymore. And so certainly with, Giada standing right there with Da Vinci, I'm sure there's a lot that they're trying to understand, and Veritas similarly, for how a planet could have started as potentially habitable and kind of devolved away. But I think understanding, not only the planet, but the star, I think understanding the stellar environment, how things could have evolved through geologic time, is something that I think would be important to assess here. And that's in fact something we want to investigate within our study, within this approach that I'm highlighting here. In terms of other potential signatures, I can't think of any off the top of my head. I mean, certainly elemental ratios, I think, could give us clues to this. And I think that's, borrowing lessons from the solar system and in current and past and future missions, I think will be valuable here.
Okay. Thanks, Tiffany.
Yeah, sure.
Awesome. Thank you, Tiffany. I think we're going to have to move along because we're running behind schedule. But thank you so much. All right. Our next and last speaker is newly minted Dr. Nick Wogan from the University of Washington, who just got his PhD. Yeah. Nick, you're going to Ames next, right?
Yeah, Ames.
Yeah, nice.
Oh, should I do this?
You just have to
click on mine there.
Yeah. It is.
Okay, and I need to talk into this.
So there's a question online if you could use the lapel mic instead.
Oh, how do you put that in my pocket?
Clip that somewhere and then get. Sure. Top two buttons or something.
Okay, so that's working, right?
Oh, share the screen.
Oh, what happened? Must have shared from the last one.
Okay. Okay.
Great, and everybody can hear me? No, you cannot hear me? Oh, this is great. Great. Yeah, it's green. And you can hear me. Okay, great. Yeah. Hi, everybody. Nick Wogan. As Giada said, I just graduated from UW, and I'm going to Ames in about a month. This project is when I did a rotation, a research rotation, or essentially an internship at Goddard with these mentors right here. So the project is called Detecting Exo-Earth Candidates, Habitable Worlds Observatory. So this talk considers a Habitable Worlds Observatory equipped with a chronograph, similar to the LUVOIR telescope concept. And I build upon the LUVOIR final report, which I know a lot of you know about because a lot of you wrote the final report. So in the LUVOIR final report, there is a strategy for finding exoplanet life. This is the upside down triangle thing people show. And I don't have the triangle, but I will quickly summarize it for you. So in phase 1, you detect exo-Earth candidates. So you detect a planet in the habitable zone, and you detect water vapor in the planet's atmosphere with a single reflected light spectroscopy bandpass between 0.83 and 1 microns. So then in phase 2, you characterize the detected exo-Earth candidates with in-depth reflected light observations. This talk is about phase 1. It's about finding interesting planets that are worthy of in-depth characterization. So this is what the data might look like if we detected an exo-Earth candidate. So this is a reflected light spectrum of the modern Earth. We have wavelength on the x-axis, planet to star flux ratio on the y-axis. The different colors are effects that molecules have on the spectrum. So like we got oxygen, we got water vapor, we got some ozone. So on the left here, we have some photometry that detects the planet. And then on the right, we have a single spectroscopy bandpass that tries to detect water vapor. You can see that big water vapor feature there in blue. Well, there's also a methane feature in this same spectroscopy bandpass. And it does not show up because we do not have that much methane in our atmosphere. But a long time ago, on the Archean Earth, about 3 billion years ago, we had a lot more methane in our atmosphere. And this is because there was no oxygen, there was methanogenic microbes producing lots of methane. And here's a reflected light spectrum of the Archean Earth. And you can see in orange a big methane feature in this spectroscopy bandpass that the LUVOIR report suggested could be used to detect water vapor. So all this motivates 2 research questions that I'm going to try to answer for you in this talk. So for a spectrum between 0.83 and 1 microns, what signal-to-noise ratio is required to detect water vapor? And what signal-to-noise ratio is required to detect the Archean methane biosignature? So quickly, some methods. So to compute the detectability of water vapor and methane, I use Bayesian model comparison with the RFAST radiative transfer code. Bayesian model comparison is a pretty standard technique for computing the detectability of a molecule. RFAST is a code written by Ty Robinson's research group. All calculations consider a spectrum between 0.83 and 1 microns with a spectral resolution of 140. And I use my one-dimensional climate model to simulate the temperature and composition of some of these habitable worlds. Okay, so part 1, the detectability of water vapor on habitable planets. So the first point I want to make about the detectability of water vapor is that it depends on the surface temperature of a habitable planet. So here we have a modern Earth-like planet. This is the water vapor in its atmosphere on the left. We have water vapor mixing ratio on the x-axis, pressure going up in the atmosphere on the y-axis. So for the modern Earth, we have a surface temperature of 288 Kelvin. The amount of water vapor in the atmosphere is dictated by the temperature. So water is very near saturation point in the atmosphere. On the right is a reflected light spectrum between 0.83 and 1 microns, and you can see a big water vapor feature there at about 0.94 microns. But the thing is that Earth has not always been 288 Kelvin. It's been warmer and colder in the past. So for example, when there were dinosaurs around, back on the Cretaceous Earth, this is like 100 million years ago, the surface temperature could have been 300 Kelvin. And since the planet was warmer, there'd be more water vapor in the atmosphere. And you can see that its reflected light spectrum has a bigger water vapor feature. Earth has been colder in the past. So if you imagine an ice age Earth with a surface temperature of 273 Kelvin, has less water vapor in its atmosphere, and the water vapor feature in reflected light is much smaller. So what we can do is compute the detectability of water vapor as a function of temperature on a habitable planet. So that's what I'm showing you right here. X-axis is surface temperature in Kelvin. Y-axis is the signal-to-noise ratio required for a 5 sigma water vapor detection. So for the modern Earth, you just need a signal-to-noise ratio of around 7 to detect water vapor. But for a cold habitable planet at 273 Kelvin, you need a bigger signal-to-noise ratio of maybe around 15 or so. So the second point that I want to make about the detectability of water vapor has to do with the habitable zone, or the light on water zone, as Kevin Zonley calls it. So here we have the habitable zone for our sun. It's between 0.99 AU and 1.67 AU. So we can throw modern Earth in this system. Here's something like the surface temperature and temperature structure of a habitable planet at 1 AU. We're saying the same surface temperature of modern Earth, so if 288 Kelvin, the top plot is the temperature structure of the atmosphere. So it's 288 Kelvin at the surface, it gets colder as you go up. And there are, of course, water vapor clouds, just like on the modern Earth. On the bottom here, we have a reflected light spectrum of this planet. You've got a big water vapor feature, which I just talked about detecting. But as you go out in the habitable zone, you dump more and more CO2 on a planet in order to keep it habitable. You need more greenhouse gases to keep the surface temperature around 288 Kelvin or just above freezing. And at about 1.35 AU, CO2 is so abundant in the atmosphere that it begins to condense in the upper atmosphere, and CO2 clouds begin to form. And this is potentially an issue for detecting water vapor. So for example, let's consider a planet at 1.45 AU in the habitable zone. Here it's temperature structure in the top right. You have the same surface temperature, 288 Kelvin. You have water vapor clouds in the lower atmosphere, but you also have CO2 clouds in the upper atmosphere. These CO2 clouds prevent light from probing the lower atmosphere where there's water vapor. And so you can see in the bottom right that the water vapor feature is diminished significantly for these planets with CO2 clouds. So to detect this water vapor feature here, you need a very big signal-to-noise ratio of something like 40. So, very, very good data. So this is the second point I want to make about the detectability of water vapor. It is probably hard to detect, or I think it might be hard to detect in the outer habitable zone because of CO2 clouds. Part 2 is on the detectability of Archean methane biosignature on habitable worlds. So we don't know the methane concentration on the Archean Earth a few billion years ago. Plausible ranges are between 0.05% and maybe 1%. So this plot here is just a couple different Archean Earths in reflected light with different methane concentrations. So for a methane concentration of 0.05%, the methane features in orange are small. But if you have 1% methane, like on the top, the methane features are pretty big. So what we can do is compute the detectability of this methane in the same spectroscopy bandpass between 0.83 and 1 microns. And that's what I'm showing you here. We have methane concentration on the x-axis in percent of the atmosphere. And on the y-axis is the signal-to-noise ratio required for a 5 sigma methane detection. So the bottom line is that for methane concentrations bigger than 0.1%, we can detect methane with a signal-to-noise ratio of about 20. But if you have a big methane concentration, say near 1%, you can detect it with smaller signal-to-noise ratios of maybe around 5 or 6. Okay, so that's all I have for you. I'm going to quickly summarize. So we computed the data quality, so the signal-to-noise ratio, required to detect water vapor and methane for a spectrum between 0.83 and 1 microns to identify exo-Earth candidates. So these are interesting planets that are worthy of in-depth characterization. Water vapor detectability depends on surface temperature. So for a cold 273 Kelvin habitable world, detecting water vapor requires a spectral resolution of 140, signal-to-noise ratio of 15. Water vapor is easier to detect on a warmer planet. Water vapor should probably be challenging to detect on habitable worlds in the outer solar system, or in the outer habitable zone, so beyond about 1.35 AU. And this is because CO2 clouds shrouding water vapor features. Finally, the Archean methane biosignature is detectable for methane concentrations bigger than about 0.1%. Detecting 0.1% methane requires a signal-to-noise ratio of 20, If the methane concentration is bigger, then it's easier to detect. So overall, I think that information like this can be factored into yield calculations like those done by Chris Stark to get a better estimate of what can be done with Habitable Worlds Observatory. Thanks.
Nick, we are still running behind schedule, but I think there's time for maybe 2 questions. So I saw back there, and then I'll come back to Leonidas.
Thank you. Great talk. I really enjoyed it. So have you looked at the 1.7 micron band for methane?
Have I looked at the 1.7?
Right.
No, I have not.
Okay.
Yeah. But I know that people in Sean Dolmaga-Goldman's group have probably looked at that band. So, yeah.
Congratulations on the PhD.
Thank you.
How sensitive is your analysis to surface gravity? If there are small variations in surface gravity from Earth analogs.
Yeah, so when I am computing the detectability, I am assuming I do not know the planet's mass. And so it is essentially, in the calculation, it is a free parameter. So even though we do not know gravity, even though we do not know mass, you can still detect molecules, methane and water vapor.
There's lots more questions. We are running behind schedule, so I think one more question. Jason says I can do one more question. All right. All right, maybe 2 quick questions.
So O2 is, it is, for the modern Earth, 20% oxygen, 21% oxygen. You need about signal-to-noise ratio of 10-ish and spectral resolution of 140-ish. And that has to just be in the part that covers the 0.76 micron O2 feature. O3, I don't know. The feature is really big for O3 in the UV, but I don't really know exactly what you need to detect it.
We'll do one more question.
Just a quick question. Which would be the distance of our Earth to be detected with this signal to noise that you require?
Oh, wait, say that one more time.
Yeah, to detect a planet like Earth.
Yeah.
Which is the distance for having this signal to noise ratio that you calculated? Did you calculate this distance or not?
Oh, like how far away?
Yeah, how far away? Yeah.
Oh, I don't know. Yeah,
I
am only computing signal-to-noise ratios, right? You could then imagine an observatory of some diameter.
Oh, yeah, because you need all this information.
And then you could compute how much time it takes to build up this
for the
signal.
habitable worlds. Okay.
Yeah.
All right, let's thank Nick again.
We're running a little more than 15 minutes behind schedule, so we can slip the end of coffee to 5 or 10 minutes after the hour, but we really need to stay on time because today is the latest talk that was scheduled out of the whole meeting. So unless you want to be here at 6:15 or 6:30 or 7, let's keep things on schedule and come back here in about 20 minutes.